Eric, I understand you've been doing some work in experimentation on the effect of reflow environments on residue and particularly surface insulation resistance.
Right. As has been discussed before, and I think you would probably use the same value or similar value that I would use. If you look at the electronics world, largely dominated by commercial electronics, 80% of it or thereabouts is no clean. So meaning that, especially in the case of a solder paste, that flux residue remains on the assembly for the life of the assembly. So when we talk about SIR, surface insulation resistance, that is the means by which we measure the electrical reliability of that residue. And if you look at the flux chemistry, if you will, when we do SIR testing or we measure SIR testing, typically we're capturing that large part of the market which is reflowing in air. Within that market, there is a minority of people that are reflowing in nitrogen. And so the flux manufacturer, when they're doing the J standard tests, they're thinking, okay, this is going to be used in an air reflow environment. So when they do those tests, they're doing it in air unless the product is specifically made to be reflowed in nitrogen. But there are, especially in the case of solder paste, no clean solder paste, rosin-based no clean solder paste, where, again, you have the majority reflowing in air, but a minority reflowing in nitrogen. So does that have an effect on the electrical reliability of that flux chemistry? And you have to look at the chemistry of the material, and you have to be knowledgeable on why would you even want to think about that. So if you look at the chemistry, there's a particular group of ingredients called activators.
Right.
And it is their function to remove oxidation, be it on the board itself, component leads, etc. So if you think about when you're reflowing in air, you have the potential of kind of what I think of as like a revolving door where you're cleaning oxides, but because you have air and heat, you're recreating oxides at the same time.
Right.
So theoretically, those activators, they have to work harder or longer or more consumed in an air reflow environment as opposed to a nitrogen reflow environment.
Right, because you have a double whammy. You have the oxygen present and you've got heat, which is a catalyst for oxidation.
Absolutely, absolutely. So, if you look at those situations side by side in terms of what is ultimately left over in the residue, at a theoretical level, you would have more activators or the potential for more activators to be left over when reflowed in nitrogen than as opposed to being reflowed in air. Then you have to take it the next step further and say, okay, why does that matter where SIR is concerned? And that's because if you look at all the many things that can affect SIR performance, board contamination, all that sort of thing, but if you're looking at just the flux chemistry itself, the material or the ingredients in the flux chemistry that can have an impact on SIR performance are the activators. So if you have more or less left over in one scenario versus the other, yes, the potential exists for some sort of difference in the SIR performance of that flux residue.
Very good. Now, one question I have for you, with the experimentation you've been doing with nitrogen, one of the areas of, if you will, controversy, discussion, however you want to put it, is what level of nitrogen to use in terms of measured in ppm O2. And, ovens have come a long way as far as containment, and there's also the matter of the purity of your source nitrogen that you're using. So, in terms of the experimentation you've been doing, what level of nitrogen have you been using?
Well, thankfully, for a lot of the reasons you just mentioned, we have very good nitrogen supply, and the ovens are very up to date and that sort of thing. So there were times, and I watched the meter quite a bit, if you will.
Right.
I mean, it was not common or uncommon to have values that were single digits for oxygen.
Wow.
So
I'm a long way.
Yeah, very convinced that we had a very good nitrogen environment. So.
Right. So and obviously, what you're finding, I'm sure, is that flux chemistries have come a long, long way as well.
Yes, yeah, and that was one of the things I'm trying to capture in the work that I have going on right now is, first of all, keeping in mind that not all chemistries are equal.
Right.
And so I have trying to capture 3 different variations. One is an ROL0, traditional type ROL0 with a traditional type residue. And when I say traditional type residue, I'm differentiating between that and, say, a residue that's been optimized for pin probing.
Right.
So I have one with a traditional residue. I also have an ROL0 with a residue that is optimized for pin probing, a little softer, a little waxier, as I like to say. Then I also have a ROL1, or a halogen-containing material, with the traditional residue that I'm looking at. But back to your specific question, we've gotten very intelligent and very good at selecting the activators. So there's a lot of confidence in how they're going to act in the residue. Also, you can never overlook, however sophisticated we become and as time goes along, can never overlook the simple, almost miraculous ability of the rosin to encapsulate and immobilize nasties that could be left over in the residue, regardless of where they come from, be it residual activators or what have you. They just do such a great job of locking everything in place and ultimately keeping those SIR values high and ensuring good reliability of the residue.
Right. Well, this is a very intriguing and very important topic. Where can we find this paper?
All of our papers, the Indium Corporation papers, are on our website, which is indium.com. And a lot of the papers specific to SIR performance are written by myself. So if somebody has a particular interest in that, they can feel free to contact me directly. They can send me an email, ebastow@indium.com.
Right to the source.
Yes, sir.
Eric, thank you very much.
You're very welcome.